Well, welcome to another RDWorks Learning Lab. I think I need my cup of coffee today because we're just about to embark on another one of these rather unknown adventures. Now, it's an area that we have tackled before. About a year ago, we started doing some 3D engraving or 3D carving using this machine. Now, fascinating as it was, it threw up quite a few questions which were difficult to answer. But having just recently done the Seriously Dotty campaign, when we've looked at how pictures are created, I think we've discovered quite a few things that might help us revisit 3D carving and maybe find a deeper understanding of the subject. Now, I'm just going to take a few moments and recap some of the things that we've just discovered. When you're dealing with photos, a photo is always a bitmap. You have to convert that bitmap to something called grayscale, get rid of the colour, and that leaves you shades of black and white called grayscale. You then have to process that picture into a form of dots, which gets it away from being a grayscale image, which has got lots of shades of grey in it, to just a straightforward black and white image made up of dots. That is the way that you process a photograph. And when you process a photograph, you set your max and min power to equal. And that way, when you burn your picture, you get nice uniform dots. Well, that was the aim, and we did achieve it, but there are lots of exceptions, as we found out. Now, there is another form of graphics, which I've called graphic, because it's this sort of already binary image. It's black and it's white, and it is already a bitmap. Now, we've already described what a bitmap is, so I'm not going to go through that again, but this sort of picture, including the text, will always be a bitmap. If it's black to start with and solid like this, it's definitely a bitmap. There is no need to convert it to grayscale because it's already a binary image. So we don't need to go through that process, but we still need to set the max and min power to equal, because all we're trying to do is burn black and white, black and white. Now, we burn a picture like this with what we think are uniform scan lines. We have not investigated this at the moment, but it is possible that this is not uniform scan lines, but because these are pixels hiding inside these black areas here, that it may well still be pixel driven. And I say that with a certain amount of confidence because, if you remember, one of the major discoveries that we found when we were doing pixel work was that every pixel drives a dot, and provided you run the machine at the right speed, you can see those individual dots, even though it's supposed to be a solid area of black. Now, I've converted this picture here very crudely into a vector picture. The one great advantage of vectors is RDWorks treats it as an uncommitted picture. At this point in time, you can either scan, cut, or dot this picture. You have the choice. If it was a bitmap, you do not have a choice. It comes in as a bitmap and you're only allowed to scan it. But with this sort of picture, if you wish, you could leave it exactly like this and you will cut round the letters and all these shapes. It'll just turn into a doily. You could decide to select, for instance, the word thank you and put that onto a different layer and select it as a scan. And in which case, if it's a scan, what will happen is the machine will go backwards and forwards, and as it switches on and off at each one of these line interfaces, between those two line interfaces, it will scan a continuous line, and you will build up the picture with a series of lines. Now, that's not the same as building it up with pixels. So that's a very, very important difference between vector graphics and bitmap graphics. The pictures that are used to derive these sorts of images are bitmaps.
And therefore, I think that we're going to be ruled by whatever we found out when we were doing our dotty photographs. They're bitmaps and they're driven by dots. And that may well explain some of the strange patterns that we were seeing in the background here. But we shall have to not jump to conclusions. We shall have to just work our way through it and see what we come up with. I keep reminding you of this because this was quite a fabulous finding, to know how the machine drives bitmaps. One of the big differences between doing a photograph or a graphic and this sort of 3D engraving work is that we have to use different power for different parts of the picture. And that is one of the clever things about the machine that it's capable of doing. It's capable of very quickly adjusting its power as it scans rapidly across here. Now, from all the conversations that I had with my good friend Chip Williams, he tells me that once the machine is up and running, it can virtually instantly change its power once it's working in this glow region, which for this machine is somewhere above 14%. This machine runs up to about 68% power before it reaches its limit, its 22 milliamp limit. This machine, which is a 70 watt machine, will work at down as low as probably about 9%. And between 9% and 13, probably 14%, we've got this very strange high frequency engraving region, and above 14% it drops into a very stable beam all the way up to 68%. We're going to be testing this machine today over the whole of that range between 9 and 68%. Now here is the characterization curve for my tube. We're not worried about this red line here, that's current, and basically that should be a straight line, and it more or less is a straight line. What we are interested in is the axis along the bottom here, which is the programmed percentage that we put in other words percent power, and this vertical axis up here, which is watts. So this graph describes the relationship between power and percent power. And as you can see, if I select 50% power, I'm not getting 50% power because it's a totally non-linear relationship. So this is a 70 watt tube and it's up here at 72 watts at its limit. But so therefore you'd expect at 50% maybe, if you've got this misapprehension, that I would get 35 watts at 50%. Well, at 50%, I'm getting something like about 66 watts. That one is blown out the water. But this does give us a problem when we're trying to do 3D engraving, because 3D engraving relies on the grey scale, the shade of grey, to develop an amount of power proportional to the shade of grey. So if we've got a mid-grey, it will select 50% power. But of course, 50% power is not 50% power. 50% power is nearly sort of 70 or 85% of the power. So there is this serious problem that we've got to deal with, where if we want good 3D engraving, we really are trying to somehow linearize this relationship between pixels and power. It seems an impossible task, but for our test purposes, we can do it. What I've got here, I've got 2 watts at 9%, and I've got 72 watts at 68%. Now that's a range of 70 watts. So if I put 7 powers into my test pattern, i.e. I'm going to put 7 shades of grey, and I want each of those shades of grey to represent a 10 watt step. So how do we go about doing that? I've gone into quite a bit of detail here because I don't want non-mathematicians to get bowled over by the potential complexity of this situation. I would like to try and explain it to you exactly what I'm doing. So my curve works between 9% and 68% power. Now that's equivalent to 256 grayscale levels. because that's the power range that I'm going to be using, and I want to exploit all of the grayscale levels within that power range. Now that power range is actually 70 watts. So therefore, very conveniently, I'm going to break the power steps into 10 watts per step. And what I'm going to do is to work out what the corrected grayscale value is for each one of those powers. In other words, I'm going to select 0, 10, 20, 30, 40, 50, 60, 70 watts. And basically, what I'm now going to do, I'm going to look at this chart, and I'm going to step up from 2 watts by 10 watts, which takes me up to 12. And at 12 watts, I'm going to look across and see what the power is on the power curve, and I'm going to read down on here and see that it is 11.5%. And then I'm going to go up another 10 watts to 22 watts and read off where that intersects with the power curve and come down here, and it tells me that it's 14%. So what I'm going to do is go across here and check out the relationship between the intersect of the curve and the programmed percentage that I need to put into the machine to get that power out. Now I've already done that donkey work, and here is the numbers, percent powers, to give me the equivalent of these outputs. So what I've now got to do is to say, well look, I've got a total of 59% power to play with. That's the range of power between 9 and 68%. And I've got 255 shades of grey that I want to fit into those 59%. That basically means I've got 4.34 grayscale increments per 1% power increase. Now that's the basic relationship that we need, and so consequently the way that we're going to use that, and that 255 divided by 59 is there, look, and that's the grayscale increments per 1%. So I've got 11.5% here, which we read from the graph, for a 10% power increment, and that 11.5 of course started at 9% power. So really all I've got is a 2.5% increase above 0. And so consequently that 2.5% multiplied by the grayscale increment tells me how far up the scale I'm going to go. But the problem is I'm not working from black to white, I'm working from white, which is 255, to black. So whatever that number is has got to be subtracted from 255. And in fact that gives me an answer of 244. In other words, those numbers will be converted by the controller into a current which will generate 20 watts. That number will be generated into a current that will generate 30 watts, and so on. So hopefully now I've linearized my grayscale into something which will generate equal increments of power. So now we're going to have to go away and we're going to have to generate a test pattern, and we'll go and do that, and I'll show you how I'm doing that. Okay, now here we are in Photoshop, and I've got the colour palette up because I just want to explain to those guys that maybe don't understand how the colour palette works, just how the picture gets on your screen and what grayscale is. And as you can see from these numbers here, white is 255 and black is 0. No light at all. Darkness, 0. So that's what grayscale is on the overall colour palette. What I'm now going to do is devise a test pattern to check out how 3D engraving actually works. So even before we start this test pattern, we know too much information already, and that makes it difficult to decide how this pattern is going to be designed. Now what do I mean by that? Well, we found out last time that if you use a small amount of power, you get a small dot. But if you ramp the power up, and we're going to go from virtually nothing with our test pattern to full power, it means that the dot is going to get very large. Now combine that with another factor as well, and that is that we're going to be digging deep into the material. And as we dig deep into the material, two things are going to happen. Number one, the power is going to decrease because the energy density decreases because the beam is actually getting bigger and bigger and bigger because it's getting out of focus. Maybe the idea of having uniform power steps is not that bright after all. But hey, let's forget about these practical problems and just stick with the idea, shall we? I'm going to make this a typical coarse, fairly coarse resolution as we did before of 100 pixels per inch. We've got black. Let's make sure it is black because we're going to draw the central pixel first, the central block of the pattern first. And sure enough, it's black up here and it's 0, 0, 0. So that's our color palette. We're going to use a pencil because that produces a nice little square hard pixel. And we'll put a pixel down just here. We've chosen the brush, which is 1 pixel. Well, that's pretty small, so we need to see it much bigger than that. Now bear in mind we've got a resolution of 100 pixels per inch. 10 pixels is only going to be 0.1 of an inch. I think I might make my pattern 15 pixels wide. 12, 13, 14, 15. It doesn't really matter what we do height wise. Let's do about twice the size. I'll go back and fill that in a minute. Now there's my first block of black. The middle black one is going to be black, but the outer ones are going to be, looking at our chart, 244. 244, 244, 244. And that's a shade of grey that we get, nearly white. Okay, well there's my pattern completed. So we don't want anything except the pattern, so we'll just crop that. Now bear in mind that is not white. White will not burn. White is actually just out here, outside the pattern. The surface is 0, 10 watts, 20 watts, 30, 40, 50, 60, 70 watts. Okay, so here's where we've got to make a few decisions. Perhaps we ought to be going quite fast to start with, maybe 200. If blowing, we're on a machine where it doesn't really matter, but we shall say yes. Scan 9 to 68, they're the two values that we've chosen, and this is the important thing, output direct. That's the thing that will bring the 9 and the 68 into play. If we don't tick that, it'll just do something like black and white, so we'll probably only get that one and nothing else. Now I'm going to use X unilateral because I don't want any confusion. What I want to do is hopefully see some clean steps. We're going to be using a 1.5 inch lens, which normally would have a typical spot size of probably less than 0.1. But because we're going to be using quite a lot of power at times, it's going to be at least 0.2. Therefore, I think I've settled on this 0.25. Seems quite a lot, but well, we'll see what happens when we try it. We're just trying to make the best guesses at the moment based on past information that we now are in possession of.
Okay, now I'm going to give you this rather strange overhead shot of the cut taking place because I'm going to do this first cut very, very slowly. So therefore, I've also turned air assist fully on just to try and keep the job cool, because we are going to be putting probably 60 watts being fired down at the job and at only 25 millimeters a second. So I'm anticipating a little bit of deep cutting and maybe even some melting taking place in this acrylic.
the reason I'm cutting these out is so that I get a nice, clean, polished edge that I can view the job through from the side. Now I'm going to run the same tests again, but this time I'm going to put the speed up to 50 millimeters a second for both of them. The bits aren't falling out because they're so hot on the edge, they're sticky, but I need that to get a nice polished finish. But as you can see, they do actually fall out. They've just very slightly got stuck in there. Now we're doing 200 millimeters a second. And I suppose while we're here, why not? We may as well go for 400 millimeters a second as well. Look at the way the debris is being shot out. Well, on this China Blue machine, you can see the simplicity of the drive belt system. It literally comes straight off the motor and onto a belt that drives the head. And there's 16 teeth on that wheel, that's all. For purposes of comparison, I'm now going to carry out the same tests on the light blade machine. Now obviously my characterization curve, my power distribution is going to be slightly different on this particular machine. You can see the two characteristic curves there. The top one is the light blade and the bottom one is the one that we've just been working on. Now, yeah, they're not quite the same, but I don't think for the purpose of what we're trying to achieve it's going to make a huge difference. The point has been proven on the China Blue machine, and I think, you know, if we needed to do a set of parameters for the light blade machine, then I would do so. Not particularly difficult, but not necessary in this particular instance. Okay, now you can see from the black nozzle that we're on the light blade machine now. I think this will run in the opposite direction. The scanning will run in the opposite direction, but it's still single scan. Even on this machine, which is a different tube, you can hear that pre-ionization taking place at the end of each end of the stroke. Now it sounds like a strange airflow that's taking place just at the end of the stroke as the cut gets shallower, but it's not. And again, it looks as though it's taking place over the first and last two steps. As you can see, we have a compound gearing system between the motor and the drive belt itself. And the shape of these pegs tells me which way the cutter's going, because that's where the arrowhead is. Well, here we've got our 20 sets of results, 10 from each machine. I'm just looking at them like this to see just what the physical appearance of them looks like. There is a difference between them. This was done with full air assist, and I've definitely got some blooming on the surface, some condensate. I was using about half air assist on these, and they seem to be much cleaner off of the China Blue machine. But here at 25 millimeters a second, I'm getting a lot of debris in the bottom of the cut. Okay, now before we rush off inside and measure these, what we've got on this picture is 3 of my speed runs from the China Blue machine. The bottom one is down at 25 millimeters a second, 50 millimeters a second in the middle, and 100 millimeters a second at the top. Now, obviously, slower means a deeper cut for the same amount of power. But what I really want you just to see is the basic success of my calibration. In other words, you can see that the steps, the power steps, are pretty even all the way across. And then if you remember, without changing the calibration, we did much the same sort of thing on the light blade machine. Now, although the steps at the beginning there on the left hand side, right at the bottom as you see, are probably a bit bigger than they should be, because the calibration at that end is a lot more sensitive. But as we get towards the middle and the top, the steps seem to be reasonably well spaced. So yeah, it wasn't a disaster. It was a pretty reasonable attempt at using the same calibration graph. The other thing I'd like you to just observe before we go looking at these under the microscope, you can see that the cuts are very spiky at the bottom, as though, you know, they've been fired at with a bullet or something. You know, these are impulse cuts of some sort, and hopefully we should be able to establish that they are related to the number of pixels that I was using, 15 pixels per step. Let's go and have a look at these under the microscope and see what we can deduce.
Now, theoretically, I would be expecting every single dot in a grayscale pattern to have its own power value allocated to it, and provided we don't exceed the capability, the response capability of the machine, we would expect to see every pixel and every pixel variation showing. Now, I've got 15 pixels per step, so at pixel 15, on pixel 16 I would expect to see a 10 watt change. Now, we haven't looked at that yet, but I'm just anticipating, if you like, what we should expect to see, because this is a grayscale system where every pixel, I reinforce again, should have its own power value. Now, I specifically did not choose the spacing between these scan lines to be anything special. Technically, I should have chosen the spacing to be that suitable for 100 pixels per inch. I did not. I chose 0.25, which is probably not even an interval or a multiple of the correct line spacing. So there is a risk that what we're going to see in these patterns is an aliasing effect, where we get some of the dots showing and some of the dots not showing. The other thing that I want to point out to you is this. On the left hand side, we've got a pattern that's done at 25 millimeters a second, and the lines are touching. Now, the reason why they're touching is because I'm running very, very slowly at 25 millimeters a second, and the power is having a chance to stay in one spot so long that it's actually burning nice big holes in the acrylic. Whereas on the right hand side, what we have is 400 millimeters a second, where the power is not getting a chance to settle at all, and so we're probably getting dots on that side which are much closer to the spot size for the lens itself, which is around about 0.075 to 0.1 of a millimeter. I did tell you that I was cutting these pieces out into a funny shape purposely so that we could look through the edge of the sample. And there we are. Look at that. We're looking through the edge of the sample. And as I run across there, look, you can see the steps going up and the steps coming down. Well, we've got some rather funny shaped peaks there. The one thing I do observe is that we have not lost any of the peaks because of the line spacing. They all seem to be there. And if we take a look at that first step, when we look at it from through the material, oh yes, you can see all the individual pixels there, look. When we look at it along, it's a little bit more difficult to see the individual pixels, scan line pixels, but what you can see are these groups of, look like groups of 2. So we've got 2, 4, 6, 8, 10, 12, 14, 16. My pattern was 15. So let's take a look at that second step there. Now we've got some funny little joined up peaks there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 maybe. And then the next one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 again. And the top one, well, now we're getting deeper, and because we're getting deeper, the beam is getting less focused, so we've got the possibility that we're joining these dots together because we've got an unfocused beam. And there's the maximum step there, and we can probably see that on that maximum step we've got 1, 2, 3, 4, 5, 6, 7, 8, which may well again be 16 doubles that are joined together. So there seems to be this strange pattern of 16, even though I've got 15 pixels. Now you saw me creating this pattern of 100 pixels per inch. Now I also took that pattern and I upscaled it, same size, but I upscaled it to 600 pixels per inch. No, this is not the same 100 pixels per inch. This is in fact 600 pixels per inch. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and one on the end, possibly 16. Hang about. That's what we had for 100 pixels per inch. This is 600 pixels per inch. What is going on? Well, the one on the bottom is 100 pixels per inch, and the one on the top is 600 pixels per inch. I mean, there is no difference in the dot pattern at all. Now here is 50 millimeters a second, and the results are in fact a little bit clearer. Now if you remember, when I did my dotting exercise, I found the most distinctive dots were at 50 millimeters a second and 100 pixels per inch. Well, this is a replication of that. And let's take a look at the dots on the right hand side there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That's a little bit puzzling considering I've only got 15 dots in my pattern. We check the next step. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Well, here we are at 100 millimeters a second, and we've now changed to 1, 2, 3, 4, 5, 6, 7, 8 peaks. 1, 2, 3, 4, 5, 6, 7, 8. A little bit more difficult to see where the step difference is now, and that's 100 millimeters a second. Now, just for comparison, I want to show you what 600 dots per inch. 1, 2, 3, 4, 5, 6, 7, 8 peaks. 1, 2, 3, 4, 5, 6, 7, 8 peaks. So again we've got this strange 8 peaks, and then we go to 200 millimeters a second, and we won't dwell on this too long because you just want to have a quick look at it. I'll do some analysis of the results. At 200 millimeters a second we can detect a sort of pattern there for each step, and if we take a look at those humps, we're now down to 4 peaks per step. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And when I get up to 400 millimeters a second, you can just about see the step changes, but you can't see any peakiness at all. In fact, the step changes are so small when I look at it on edge. They really do not exist. You can see there as we come out of the bottom of the picture from maximum stepping down again, there's virtually no step difference at all. Well, here we are with the light blade machine at 25 millimeters a second, and I think you'll see on the left hand side the the lines are slightly cleaner. The power supply on the light blade machine is a much crisper, faster responding power supply, and again on the right hand side, faster speed, smaller dot size, so much thinner lines. Well, here's what 25 millimeters a second looks like on the light blade machine. Now, unlike the China Blue machine, we've got some very definite peaks here at this slow speed. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Well, here's what it looks like at 25 millimeters a second when we look through the side. Again, we've got no aliasing that I can detect there. We've got complete rows of little soldiers, and they're very sharp peaks. And again, when we look at the 600 pixels per inch, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. But these are a lot cleaner peaks at maximum power, which again I think tends to reflect the performance of the power supply and its ability to supply very, very sharp pulses. Okay, now this is the light blade machine, and I'm just showing you this picture so that you can see the effect as we move from 25 at the bottom right hand corner to 50, 100, 200 and 400 millimeters a second. You can see the difference in the depth of cut and the quality of the cut. Well, I'm now going to go away and try and tabulate the results and try and make some sense of what these numbers mean, because the last time many people thought that these pulses that we were getting here were attributed to the stepper motor and the belt. Well, here's a summary of the observations that I've made on these patterns. Now, what I'd like you to do is to follow the yellow highlighted lines. Let's start at the top. 25 millimeters a second was the traverse speed that I was using, which basically was equivalent to 40 milliseconds for every millimeter of travel. Now, I was using 100 pixels per inch for my swatch, which basically meant 1/100th of an inch per pixel. I designed each step of my swatch to be 15 pixels wide, so basically that meant it was 15/100ths of an inch, or 0.15. If I turn that into millimeters, that comes out as 3.8 millimeters, and I've turned it to millimeters because that's the unit that the machine works in. So it follows that at 25 millimeters per second, the time taken to travel 3.8 millimeters is 40 milliseconds per millimeter times 3.8, which is 152 milliseconds. So that's a unit of time which I'm working in, because I think all of this revolves around time rather than distance. Right, now let's go back to the beginning. I was expecting every pixel to be given a power and every pixel to be squirted at the pattern. That appears to be the case at 25 millimeters a second and 50 millimeters a second, provided I don't go more than 100 pixels per inch. Now, before we go down and look at the rest of the results, I want to jump up to the pink line above, and I want to remind you that when we were doing the dotty results, I was able to see clearly all the pixels available when we were running at 50 millimeters a second and 100 pixels per inch resolution. Now, if we convert that 100 pixels per inch resolution to a peak-to-peak time, it comes out at 5 milliseconds. Now that's rather interesting, isn't it? Because if we start looking down at 50, 100 and 200 milliseconds, we find that the peak-to-peak times are about, but not specifically, 5 milliseconds. Now I'm wondering whether we're hitting some sort of time barrier. Now that time barrier cannot be the response time of the two high voltage power supplies, because the light blade was far and away more responsive than the China Blue machine. And if that was the case, that it was able to respond to 600 pixels per inch, then I wouldn't be seeing exactly the same peak to peak time as I'm seeing on the China Blue machine. So I'm going to discount the power supply as being the cause of that time limiting wall that we've hit. Now, my previous work with 3D engraving showed exactly the same sort of peak to peak marks, gear teeth, call them what you want. Now, there were a lot of people that had suggested to me the obvious was that I should be looking for a correlation between the gear teeth on my pattern and the gear teeth on the belt or the drive pulley. Well, I had nothing to compare it with at that point in time, and I couldn't make those numbers match up with anything. So it was an unanswered question. These results begin to answer that question. I don't think that these marks are anything to do with the belt or the stepper motor itself, because if they were, why do I get exactly the same results on the China Blue and the light blade machine? Now, I've already showed you the way in which the light blade gearing is working, and it's significantly different to the China Blue. And so the chances that these marks are anything to do with the stepper motor resolution or the gear teeth on the pulley, no, I can't believe that. One pulley is 16 teeth and the other pulley is about 42 teeth or more. I think I've got to blow that one out the water. I've looked at these results in terms of peak to peak times because I believe that time is somewhere involved in the answer. We shall find that if we divide 4 pixels into 20 milliseconds, we shall get 5 milliseconds per pixel. So that was what I could see very clearly on my dotty experiments. Go faster, and it tended to disappear. Now let's just put that in perspective with the 25mm 100 pixels per inch and the 50mm 100 pixels per inch. At 50mm 100 pixels per inch, we get again 5 milliseconds. It's happy to produce me that same pattern, and I can get a pattern which is even better at 25mm a second, which is even slower. So there's plenty of time for the pattern to be resolved. Now if we start running 25mm a second at 600 pixels per inch, what does that do to the time available for a pixel? Well, the answer is it's 1/6 of 10 milliseconds, and 1/6 of 10 milliseconds is only 1.7 milliseconds. I'm going to make a bold claim that the system cannot handle a response time of 1.7 milliseconds. Not the power supply, because the power supply, I think, is not capable of doing it either. But I don't think it's the power supply that's the problem, because the power supply is not limiting. It's somewhere in, I believe, the RD software algorithm. Now that algorithm knows, first of all, how many pixels per inch we've got, because it's busy interpreting the picture that's on the screen. It knows what the resolution of them is. It knows what the speed is, and so it can calculate approximately a peak to peak time for each pulse. Now, if it thinks that the pulse time is too small, what it does, I'm proposing, is that it chooses a resolution that can suit itself. At 600 pixels per inch, it averages 6 pixels into 1 pixel and says the average power for those 6 pixels is, and it gives an output. So my point really is that when we get to something like 100 millimeters a second and we start doing 100 pixels per inch, the machine is just not capable of achieving that speed. So it does an averaging over a number of pixels. Now, as it does that averaging over a number of pixels, what it's going to do is to destroy the step resolution between the pixels. So you're going to get a much coarser, less refined picture. Now, I don't know whether that is the case or not, but certainly the evidence that shows from my results says that the faster you go, the less sensitivity you can see in the results. And in fact, when we get to 400 millimeters a second, there were no peaks there at all to be seen. There was no depth change between the steps at all.
Well, here we are back in front of my favourite blue toy. These little strips have given me a possible insight into the way 3D engraving works. Now, it might be controversial. I think it's probably a different take on things that you might have heard before. In fact, if you've ever heard anything before on 3D engraving, if you're some sort of expert in this field like Kearns, then maybe you fully understand because you have written the software yourself. You know how the software works. I don't. I've got no idea at all. I'm just second guessing what must be going on because of the consequences of what I'm seeing. That's all I can do as an engineer, look at the evidence and try and deduce what might be going on to produce that end result. Now, I've done that, and I'd be interested if anybody else has any different ideas. But I'm not going to stop there, because what I've found so far tells me that I've got quite a lot more work to do. And as I do that work, I hopefully will be able to prove more and more whether or not what I've deduced is anywhere near the truth. Now, the first thing that I've got to do is to look at my calibration graph and decide how we're going to use that in future. Because, to be honest, using 70 watts is just totally unacceptable. As with most engraving, you only need a small amount of power. Well, we are doing some digging, some cutting. We're burning away. So we do need some power. I don't think we need anywhere near the 68% power, 72 watts, that I was throwing at this job. I think in the next session, we're going to be looking at this little slope here and working out just how much power we really need to do a job. And then we'll divide that power into much smaller increments. And it means, because this is a linear part of the curve, I won't need any calibration corrections. And because we're not using as much power, we shan't get as many spikes, I don't think. We shall get much rounder little pieces. And we're not going to be running fast. I think to keep the definition up, we need to run quite slow, like doing the dot program. When we were doing dots, we had to run slowly to get a real, proper dot picture. Anything else was a bit of a fudge that seemed to work, but it was not a dot picture. Now, I think maybe the same sort of thing applies to this list of characteristics that I've got here. It certainly seems an absolute waste of time to try and use 600 dots per inch. It looks as though you really probably need to work with nothing more than 100 dots per inch. Otherwise, you won't be able to get the resolution into your picture anyway. It will always default back to basically 100 dots per inch. Another interesting set of discoveries. Getting closer to the truth, I'm sure. And next time I hope we'll be able to pin it down. So until then, cheerio.